All right, why don't we go ahead and get started? Welcome back, everybody, to Python for STEM. I keep forgetting to call you guys Pythoners. Welcome back, Pythoners, to Python for STEM. Practice makes perfect, right? So you should be able to see my slides, right? And my pointer. Very good. Cool. So welcome. Today, we're going to introduce a new topic, completely different topic. So if you missed the previous lectures, shame on you. Just kidding. You can go back and watch them. They're on YouTube, and they'll be there for us as long as we can, for indefinitely. But the topic that we're going to cover today is unrelated to everything else that we've seen. So just go watch them, but you don't need to know what was covered there for you to make sense of what we're going to talk about today. So don't fret. All right. So today we're going to actually introduce calculus. Hey. So if you've never seen calculus, welcome to your first calculus course. It's going to be pretty easy. We're going to make it fun and easy. If you've seen calculus, some of the stuff will be repetitive, but it's okay. You hear it from me. And then hopefully you'll get to see some new stuff. So we're going to get to differential equations. We're going to talk about how to solve them numerically. It turns out that it's much easier than what is typically done in calculus courses, because everything is easier if you can do it numerically. That's the idea. So first things first, if you want to have access to our Dropbox folder, to the Slack channel, to all the recordings, yada, 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 and you want to have access to all those links, instead of taking a screenshot, what you can do is just email us at pythonforphysics@odu.edu. That's pythonforphysics@odu.edu, and you'll get another reply with all these links. All right. And as always, we want to start by hearing how you're doing. It's been a long summer. It's hot in some places around the world where you're at. Why don't you tell us where you are coming from and how you're feeling? Are you enjoying this class? Are you enjoying REYES? I know that the bulk of REYES already ended, but there's lots of videos. I mean, we covered so many sessions. I'm still watching the videos because I couldn't attend all the sessions, so I'm still like going back and watching all the things that we hosted, and my colleagues, the speakers that they invited. So hopefully you're doing the same. And if you aren't motivated enough to go check out the videos, just know that we're still gonna do the trivia night. We just decided to postpone it a little bit because we generated so much content, so much cool content, that we wanted to give you time to catch up and absorb it. So hopefully you're going through it systematically, learning all the stuff. So give us any feedback that you have about that, and we'll let you know when trivia night is happening. Another thing that I should mention is that the mentoring acceptance letters are going out. So if you apply to the mentoring program, you should be hearing from us soon. And I'll be hosting some lectures to my mentees, which is a lot of you, starting Monday. So do we have any comments on the chat, Connor, that you want to read?
Yeah. So I guess I should start with whoever asked first. So Philip is asking, for the mentorship program, should we reply to the email with the forms that you required?
Yes, please. If you received an email from either me or the REYES team, please reply with the signed forms that were requested.
All right. And I think this is in response to your how are you doing question. Abby had to debug for 2 hours. Not the funnest of experience, but I at least I learned something. Wait, hold on. But at least I learned a lot of new things.
Yeah. That's great. Coding is a lot about debugging. I mean, it's really great when you do things fast, but it's when you're writing code, you want to try to be as slow and meticulous as possible, take as many notes so that you don't introduce bugs along the way, because bugs can just consume your life. Yeah.
All right. Yeah. Adriana is tuning in from Arizona, and they're doing well today and excited to work on calculus.
Woo! Me too, Adriana.
All right. All right. And Anonymous is asking, have the emails for all the mentors been sent out?
No, I think not all, but they should be being sent out by the end of today. I've sent mine, but I think others are still sending them out.
All right. Another Anonymous asks, is it hard to be accepted in the mentorship program?
It depends. So there might be some people that may not be matched with their preferred mentor. So we had around a little over 20 mentors, and some of them can't mentor that many students. And so we had over 200 mentees. So that has made it hard for us to match. But what we're allowing folks is that those that don't get matched with their ideal mentor, they can work with me in my lecture series, which I'm going to be co-hosting with my collaborator, Andrew Jakura, Dr. Andrew Jakura. So we're going to be basically teaching folks about the basics of nuclear physics and programming in the context of nuclear physics. So if you don't get to work with your ideal mentor and you still want to learn something new, and you can work with us. So that we're not putting any limits on.
Yeah, we're getting a lot of questions here. They're coming in about as fast as I can read them. All right. Philip says it's been very hot in Greece, but is otherwise doing well. Yeah. And we have somebody else who's from Greece, but lives in Glasgow, and they're excited to learn more Python.
Ooh, yeah. Great.
And Aditya says you could say the topic we're learning today is a bit derivative of Newton's work.
Oh, pretty good. I like it. Very clever. All right, let's jump in. I like the Greek representation. I love Greece. I've been there. I've been to Thessaloniki and Athens. Oh man, I left my heart over there. Okay, so let me jump in. Let me start with the review of what we covered last time and see if there's any questions about that. So we left you with a set of exercises where we introduced Breit-Wigner distributions, right? Which are these energy-dependent distributions, which are very common in particle physics, and they're used for describing systems that are resonant, and they are what is used for hunting particles in many cases, and they have these like little bumpy like behavior as a function of energy. And so we asked you to make plots for them. So very simple, right? By now you've learned about making functions and making plots, and so this shouldn't have been too much of a challenge. Then we introduced the notion of fitting, which is just universally useful, not just for physics, but just about anything out there in science in general requires, if you're going to analyze any data, a lot of times you're imposing some functional form into your data. The mechanism that you do that is through routines that fall under the name of fitting. And that required us to define a function called a chi-squared, which is a goodness of fit. And this is a function that is minimized when you pick ideal parameters of your theory that best match the behavior of your data. And so we explain how to do minimization, a simple way to do minimization in Python. Of course, there's a lot under the hood here, but that's okay. We're not learning. This is not a computer science course. This is a science course where we're using computer science to work in our benefit, right? And so I asked you to use code to write code to minimize functions using the minimize function inside of optimize, which is inside of on SciPy. Then I gave you some data, some mock data, some fake data, where what I asked you to fit was just a constant. So the simplest thing we could imagine. So I gave you a constant that has been determined by a bunch of people, some fake people, and each constant has an error. And so all you had to do is just fit this fake data by constructing a simple chi-squared, which is just defined by the difference between your data and the constant you're trying to determine, divided by the uncertainty of the data, all squared, and then you sum over all possible elements in this list. And so hopefully you get a constant that is close to 100, because that's the number that I used to generate this data. Sorry, 1,000, because that's the number that I used to generate the data. So that was just a warm up, essentially, just to get you warmed up. Then next, I created this like really complicated story that was, somewhat fun and physics motivated, to basically get you to fit a linear, just a straight line, right? So, and I told you this long-winded spiel about nuclear physics and simulations, and I gave you some real data, but this is just data that was just basically a straight line. The straight line describes the mass of the proton as a function of the parameters of the universe, which these simulations are able to vary. And I told you some story that when we take these parameters to 0, that would be the limit where our masses are completely determined by nuclear physics and not determined by Higgs, the Higgs boson. Here is the value, the experimental value. And so if you were to able to do a straight line fit to this data, you're able to calculate the intersection with the limit where the quark masses are 0. And so you're able to see the difference between the value. This is an experimental point. This is what the nuclear mass is, the proton mass is. And so you're able to see this gap, which is roughly around 15% or something of the mass of the proton, can be explained due to the Higgs. And so this is all to say that our mass is largely driven by the complicated dynamics of quantum chromodynamics, and to some lesser extent due to the dynamics of the Higgs. So the Higgs is not the source of our energy and mass, although it does give mass to quarks and leptons. The source of our mass is due to the dynamics of QCD, and that's just an outstanding, really interesting problem. And so, and the last exercise was I gave you some fake data of some Breit-Wigner distribution that I generated with some arbitrary separations between the points and some uncertainties, and I asked you to fit this data. So you should have gotten in like a curve like this, and hopefully you've got in there. So, and these were the equations, the main equations that we presented. Are there any questions about these exercises? Have people been able to start working on them? And like I said, they're not necessary for what we're gonna do. We're not gonna do any more fitting here, but I still wanted to take the opportunity to answer questions that might be, if there's a question out there that is puzzling you, I'm sure it's puzzling other people. And so,
yeah, we have some good questions here. Well, Adriana is saying that they've had trouble defining the right loops to calculate the chi-squared function and then to minimize that function. For the code you show on the minimization previous slide, can you show us the complete code for that? It seems like a function is missing from that one. I watched the recording and you said a function that I defined previously.
I imagine this is the one, right?
Yeah, I think that's the one they're talking about.
Very good. Yeah. So here, we can write a little bit of code. All right, so here what's happening is that I define a function called chi-bw, and it depends on a list of numbers, which are 2 numbers. So I pass these two numbers, I pass this list, and I break it up into two numbers, okay? Then that gets fed into another function, p underscore bw, which I define elsewhere, which is in my code, by the way. So this is all on the Dropbox folder. Sorry, my Dropbox is a mess. I shouldn't have showed you my Dropbox because it's such a mess. And I'm ashamed of it. There we go. All right, which folder is this in? This is project 4, right? You have Raul's code, fit exercises. So we can look at that. Let's close this. Save. All right. P. Yep. And make it bigger. Yeah. So here's the full code. So it's in line 170. That's where the minimization routine for chi-squared begins. So this defines the Breit-Wigner distribution as a function of energy given gamma, m and gamma. Okay. So that's that. All right. Then these x's and y's are some global parameters, which I defined down here. Okay. So m and gamma are the mass and width of the state being fitted. Okay. So here we are writing this as a combination of 3 terms. This is the numerator. Okay. So 2 terms in the denominator, 2 terms in the denominator. I don't know how to spell. And then 1 term in the numerator, okay? Then, so this is a Breit-Wigner distribution, right? Then this gets called over here. You see it, right? And so XS is a global array that holds the energies of the data. All right. And so this chi-squared is a function of m and gamma. The x's have been globally constrained, so I don't feed it into the function, okay? And the y's is a global array that holds the data, the distribution that, yeah, distribution for the reaction. Okay. And then SIGs is the standard, is again a global array that holds the uncertainty for the y's. All right. And so then now you see I have no for loop. I have the PIs, which I define over here, right? So this depends on m gamma, but also the global array of the energies that gives me back an array. Now P is an array of the same size as YS. Of SXS, ys, and sig s. They're all the same length, okay? And so then this thing right here, this difference right here, I'm taking the difference between the expected value of the data, this is the actual data, divided by the standard deviation. So let's look at the expression. So I have my general definition for a chi-squared over here, right? So it's the actual data minus expected value of the data, which depends on the parameters, divided by the standard deviation. That's exactly what I have here. I just flipped the order, but that doesn't matter because I'm squaring, right? So if I have a minus signs difference, this is going to give me the same result as this because I'm squaring it, right? So the square of -1 is equal to 1. All right, and so then I square this whole puppy. I grab this and I raise it to the second power. It just squares each element, and then I sum over the whole thing. This is unnecessary. This doesn't do anything, and that gives me the chi-squared. So then that is what returns the chi-squared. Then this thing gets called in the chi-squared minimization function. I have to give it some guess for my parameters for m and gamma, just some list, which is my guesses. I feed it over here, and then this chi-squared has to be a function of the same list of the same length, right? So it is, right? That's the way that's the one subtlety that I didn't mention, that this function will minimize. So minimize will minimize the chi-squared function, assuming that you give it some guess parameters that are the same length of the input parameters of the size of the list that is the input for the function you're trying to minimize. All right, does that help answer the question?
I'm not sure yet, but
all right.
Oh, yep. They say that helps so much. Thank you.
Great, awesome.
All right, and Characlia says that they're in Thessaloniki now, and happy to hear that. Hope to see you someday. So I guess they're talking about
Greece.
Greece, yeah.
Yeah. Yeah, maybe someday we need to have a Thessaloniki REYES program. We've been talking about taking REYES global, so maybe we need to go to Greece someday. Yep, that'd be a great place to go eat. Okay, so let's dive in. So that was my review. Unless there's any other clarifying questions, let's dive into new types of math. So we're just going to do math today. So where are we going? Well, so by the end of next week, we're going to start talking about differential equations, which serve as a model for thinking about infectious diseases and the evolution of infectious diseases. So Professor Ted Rogers will probably be the one lecturing about that starting next Friday. So my goal is to get you to the point where you'll be able to follow that. And so to do that, we need to start from the basics. We need to start from the basics of calculus. And so what we're interested in is understanding how functions change as you vary different parameters, okay? And that's really the bread and butter, the foundation of calculus is how do we calculate the changes of functions and the rate of changes of functions. So here, let's consider a function f, right? And it depends on some independent variable x, okay? And some of this I'm going to have to be pedantically slow, but we'll pick up, don't worry, okay? So let's say that at some value at some point in x, given some value x1, this function has some value, and then at a later time, x will be changed to x2, right? And so the change in x, we're going to denote with the Greek letter, the capital Greek letter delta, sticking to the Greek theme of today, right? So delta x, capital delta x, is the change in x, which is just the difference between x at some later time, right, at some later instance, minus the original value of x. Well, we can do the same change, right? As we change x, f itself is going to change, right? And so the change in f, well, we're going to denote it the same way. Delta f is equal to the f evaluated at x2 minus the previous values of f, which is given by evaluating f at x1, okay? And this triple line symbol just means it's the working definition, okay? So this is the definition of delta f, this is a working definition of delta x. And so at times, we'll want to specify the shift in f in a particular way. And here we're gonna, what we'll do is we'll start by a lot of times defining the shift in x center around one point, and we're going to be using a separation scale, which is going to be which we're going to denote as a. Okay, and so all this means is that we're going to define the original x1 as x minus a, and the final x2 as x plus a, okay? This means that this is just another definition of a, so this is just a definition for a, and what this is going to tell us is that the difference between x2 and x1 is equal to 2a. I see that I have a little typo, so let's fix it while I'm here. Oop. Perfect. All right. And so given this definition, right, then the change in f is just going to be f evaluated at the later point, which is x plus a, minus f evaluated at the original point, which is x minus a, right? Just from these definitions over here. When we're going to want to make this a dependence explicit in the difference of the functions and the change in the functions, sometimes we'll use this subscript a, just to emphasize there's some a dependence. And this is going to be useful when we're considering numerical evaluations of this and we want to take a to be 0, okay? So that's that. Okay, why do we care about describing changes of things, right? Well, the first example that we all encounter where we start thinking about the rates of change of quantities is when we start describing moving objects. And in fact, there's a little bit of this that we've already assumed in some of our exercises, and perhaps we could have started with this instead of just jumping into kinematics, right? But well, nevertheless, we're moving things around. But when we're describing the motion of particles or objects, people, etc., right? We always have some sort of descriptive question in mind and a descriptive quantity that tells us, it quantifies that answer. And so a question could be, where is the object located? And the answer that we would be seeking would be in the form of a position, right? It would be telling us where that object is, in fact. If we're interested in asking how far the object has traveled, then this is telling us something about a change in position, right? A change, some distance that has been traveled, or some displacement. Okay. And if we're asking where is it going now and how fast is it going, then the answers, the descriptive quantities that would describe this are in the form of either velocities or speeds. And we'll touch on, what each one of these mean specifically. But then if we want to ask whether the object is speeding up, slowing down, or neither, then the answer is in the form of accelerations. Okay. So this is the first example where we encounter rates of change in describing objects in nature. But of course, there's other ones, and that's, we're going to touch on these specifically when we start going into infectious disease models. So maybe just to remind you some of the basics of when we think about the locations of objects. So if we want to locate a position, we always have to define some frame of reference, and mathematically or graphically, the way that we do this is by saying at some point we pick to be the origin, and then we design some direction to be positive and another direction to be negative, right? And then depending on the where we locate the object, then we can say we can exactly then say where the object is located. We can say, for example, in this case, the point is located at 2 meters away from the origin towards the right. Right, that's what's telling us. The fact that it has a plus sign. If it's a minus sign, well, it would tell us that this object is 2 meters away from the origin, but towards the left. Okay, so when describing positions, the signs are absolutely critical. Now, if we want to understand displacement, right? So when an object has traveled, things start getting a little more subtle, because you can either talk about distances, which is the total distance that has been covered. So the total ground that has been covered, sorry. So distance is the total ground that's been covered, versus displacement, which is a vector, which is telling you where you started. So the relationship between where you ended compared to where you started, okay? So more specifically, imagine that you started at 0 and then you went to 2, meaning +2. Then your distance is so the displacement in this case is positive because you've gone towards the right? So the displacement is just your final position minus your original position, which is also equal to the distance that you traveled, okay? But in the case that you go from the origin to the left, 2 steps to the left, then your displacement would be, because you're in a final position that is negative, your final position would be -2, your original one would be 0, so you have -2 minus 0, which is equal to -2. So the displacement is negative, okay? But the distance is the same. You've covered the same amount of ground. And so in these 2 cases, the distance is the same, but the displacement is different. And that's critical. That's a critical distinction. So for example, if I were to walk around my room a little bit, so here, let me shuffle around. I'm in my chair and I'm like shuffling around, right? And I move for a while, right? And I end up in the same point. All right. Then what would be my displacement? Anybody? 0. Anonymous got it right. What about my distance? Is it 0? Not 0? Yeah, the distance would be something. It just wouldn't be 0, right? I don't know what it is. So distance and displacements are in general very different, right? Displacement is a vector, distance is not. So let's say that we have a car that is moving, that a car moves 72 kilometers towards the right, and then reverses and travels 120 kilometers to the left. What would be the displacement of this car? What would be the distance traveled by this car? Let's see if anybody. This is a question for you guys. I got some questions for you. So you're welcome to answer them in the chat. So I see. So for
most people are saying F or -48.
all right, for the first one, very good. What about the distance? Ooh, I thought I was drinking water. That was coffee.
All right, there's like consensus on C, from what I can see.
Consensus on C. What do you think? Is it right? Sounds about right. Yeah, let's do it. There we go. So you guys are too sharp, too good. So yes, the displacement, right, is the final minus the initial. You your final position is -120. You're so well, you have to do, you can break this up into two stages, right? The displacement here followed by the displacement here. And so you end up with -48. The distance would be the sum, right, of the magnitude. So it would be this distance plus this distance. So you end up getting 72 plus 120, which is equal to 192. Too good, too good. All right, let's jump ahead. Let's jump ahead. All right, so if we want to start describing the motion of objects, right, then you have to tell us not just how far you've gone, but also how fast you're going, right? And so the simplest quantity you can think about calculating is speed, which is the average. On average, the speed is defined as the total distance that you traveled divided by the time that it took you to cover that distance. Okay, so this is a first simple intuition, right? It tells you a lot about the distance that you cover, right? And you want to know about the time, right? And so that it makes sense, right? It's telling you about how fast you're going from one point to another. Speed and velocity are closely related, but they're not quite the same. Okay. The simplest distinction is that you're dividing distance by time, both of which are scalars, and so you're going to end up with a scalar. All right. Velocity, on the other hand, it's not just telling you how fast you're going, but it's also telling you where you're going. So it's actually a vector. All right. And by now you're somewhat familiar with vectors. So they're just, it's an array in Python world, right? So examples of velocities could be 30 miles per hour east, 2 meters per second up, 25 kilometers per second towards Richmond, right? The speed can be the magnitude of the velocity, but it is a scalar, all right? And so the average velocity, the way that we can define the average velocity is the displacement divided by the time that has taken for you to take that displacement. So the displacement is a vector, right? You're dividing by a scalar, which is a time lapse, and so that's consistent. And so it would just be the difference in positions divided by the difference in time. Notice that we're using this delta notation for denoting the change in x as well as the change in time. The dimensions of velocity, right? It depends. These are dimensional quantities, so it depends on the dimensions on the numerator and the denominator, right? Which are meters per second, which are the same as speeds. And as always, this bar notation just means the average. We've used this a little bit, but it's worth emphasizing it. So there's a little bar just tells you that you're taking the average. All right, so graphing velocities, this is going to be useful because this is an example of a rate of change, and we're going to be plotting rates of change in general for general functions. So imagine that at some point in some t1, which is set to be 15 seconds, so that's your original time, your position is equal to 60, right? And at some later time, you're being 30 seconds, your position has been shifted to 120. So this here we plotted the original position at the original time, right? 15, 16, 60, and then at 30, you're 100, 120, right? And so imagine that you're going at a constant rate. This is what you would be, this would be your position as a function of time. And so let's look a little bit closer at this. And what we can see is that the change in time is just let me just build it up. So what you can see is that the rise is equal to a change in position, the run is equal to a change in time. And so if we remember that the velocity is just a change in position divided by the change in time, that's nothing more than the slope of this graph, right? The slope is equal to the rise, meaning the difference in height, divided by the run, which is the difference in width. Okay, and so in this case, we can just graphically, envision the slope of this graph telling us about the velocity, and we can just go ahead and calculate it as well. All right, very good. So this is easily generalizable for not just when you're going at a constant rate, but when your rate is changing. We can still calculate the velocity and the speed, but this would have to be what we would in general want. I mean, not always, but in general, what we would want to calculate is an instantaneous velocity, meaning how fast you're going at that specific time. And the way that you would calculate that is, let's say that I'm interested in at the specific time P1, right? Well, I can approximate the velocity by just looking at the height over run for some specific point, and then just start to shift that point closer and closer and closer to my my desired point. And so we can start imagining that what I'm taking is a limit as this P2, which I replace with Pi, starts to get increasingly close to P1, which amounts to taking the difference between the times, right, this delta t, to 0. All right. Of course, the height is also decreasing. So you have a height that is, because I'm going from this height to this height to this height, and it's decreasing in such a way that the run is decreasing, and these two are decreasing at similar rates in such a way that this limit is well defined. Okay, mathematically, we denote this limit. So this this limit where delta t is going to 0 as dx over dt, right? The delta is essentially the Greek letter for d, right? So we just replace a delta with a d, telling us that we're taking this limit. This is known as a derivative, which is the working definition of a derivative is this. It's just taking the limit as you displace a function divided by the independent variable, the displacement on the independent variable, and taking that to 0. Okay, that's essentially all a derivative is. It's just a symbolic placeholder for that limit. All right, very good. So there you go. This is your first calculus concept. Welcome to calculus. All right, let's move on, and then we'll solidify these things even further. So acceleration is the rate of change of velocity. All right. So if the velocity is not constant, it's changing, right? You're driving, you hit your accelerator, and then you go from 0 to 60, right? As you go there, you're speeding up, right? And so you're accelerating. This also is a vector because the velocity itself is a vector, and the way that it's defined is as the change of the velocity divided by the change in time. And so it's that simple. You just grab the velocity at some later time, subtract it from the velocity at some initial time, and you divide it by the change in time. That's it. Nothing crazy. And so, for example, imagine that I have some car that is moving at 50 meters per second and it slows down to 5 meters per second in 5 minutes, right? Then what would be the acceleration, the average acceleration of the car? Well, it would be the final speed minus the original speed divided by the change in time. The final speed is 5, the original one is 15. The difference between this is -10, right? And then on the bottom, I have 5 minus 0. And so I have -10 divided by 5. Even I can do that. That's equal to -2 meters per second squared, right? And those are the units of acceleration, right? It's the units of velocity divided by the units of time. All right. So the acceleration can be negative, right? In this case, because the velocity is decreasing, and so the object is decelerating. So maybe here's a conceptual question for you. If I have an object that has 0 acceleration, does that mean the velocity itself is 0? I see somebody already. All right, I get a lot of no's. Very good. Yes, the acceleration is the rate of change of the velocity. So when the velocity itself is 0, the change in the velocity is 0. It means that the velocity is constant, but it can be whatever number. It doesn't have to be 0. So it doesn't mean that the velocity has to be 0. So perhaps some of you put maybe, thinking like maybe it could be, but that would be meaning that maybe this means this, but we know that definitely it doesn't mean that. It could be 0, but it doesn't mean that it has to be 0. All right. So, okay, so that was average velocity acceleration. So how do you define instantaneous acceleration? Well, take limits, my friend, right? Same thing, right? You have the acceleration that we know the acceleration is equal to the change in velocity divided by the change in time, right? Just do the same thing that we did before. We take the acceleration at take the acceleration by evaluating the velocity at some later time compared to the original time. And then we take the limit as this time gets closer and closer and closer, right? And so this limit, well, it's the same kind of limit that we considered before. Sorry. It's the same kind of limit we considered before, where we had the change of some function on the numerator divided by the change of the independent variable in the denominator, and we're taking the limit as that change of the denominator is going to 0. That is nothing more than dv over dt, the derivative of velocity with respect to time. Good. Are there any questions about this so far? This might be a review for some of you, but it might be really new for some of you. So feel free to shout out and see if you have any questions that are unclear.
Don't have any so far, but maybe they're still typing.
Yeah, we'll give them a second. So maybe while you type, I mean, what I've given you is a little bit of an example of why calculus matters, right? In describing the motion of simple objects. Calculus is just universally useful though. I mean, calculus is just everywhere. And so we're gonna take a step back and just start abstracting things a little bit, right? And just think about some properties, some basic concepts in calculus that perhaps you've seen already, but then we're going to start testing your numerical abilities to test these ideas. Okay, that's where we're going. And so calculus is, as I said, just a remarkably powerful field in mathematics and math. And its history dates back quite a bit, but the formalization of the field is largely attributed to Newton and Leibniz. Leibniz interest, so you can see these two folks over here. Leibniz interest was mainly on foundational notation and mathematical rules. Newton was basically just interested in using calculus as a tool to be able to describe physical phenomena, which is what drives a lot of us towards calculus, but really calculus is just generically interesting. And roughly the way that calculus is taught is that it can be to first approximation separated into two subfields, I guess. One, which is differential calculus, where the main thing of interest is the rate of change of quantities. And hopefully, as already is a little bit evident, this amounts to evaluating the slopes of functions or the curves of functions, while integral calculus is interested in continuous sums of functions. And we may or may not have time to talk about how this can be useful, but it amounts to equivalently to evaluating areas under the curve of functions. And in fact, in the project that I plan to have with some of my mentees, and in fact, Connor has worked quite a bit on this, a lot of the things that we are interested in these days in our research program is evaluating integral equations. So we're going to talk about differential equations. A lot of what we've done recently has been amounting to evaluating integral equations numerically using Python or similar languages for physically interesting but complicated functions. And so there's still a lot of research going on involving just the evaluation of complicated integrals. All right, so we're gonna focus on the rest on differential equations, in particular, so the broader field of differential calculus, which is what we already started touching on. And so whether I'm interested in evaluating velocities or accelerations or the rate of change, the number of COVID cases per day, in general, what I'm considering are derivatives of functions. Okay, this symbol d over dx of some function, which is just defined as the change of the function divided by the change of my independent variable, which we're going to be using this notation where the separation between the initial and final point is a distance of 2a, okay? And I'm interested in the limit where this distance between the 2 points goes to 0, which amounts to just taking a to 0, okay? And so what we're going to be evaluating a lot is the limit where you evaluate the function as some step up minus the function evaluated as some step down divided by twice that step, okay? This is, of course, the instantaneous rate of change, but this is, in general, not an easy thing to evaluate analytically. And in fact, that's the whole point of basically this first semester of calculus, is teaching you how to evaluate this analytically. But numerically, this is very easy. And it's going to take me just one course, basically, to teach you a lot of the things that you would learn in calculus, in a formal calculus class, just doing it numerically. So, in fact, here's your first exercise. You can start doing it. I don't have to, there's like very little that I have to, I'm just basically wasting time chit-chatting here. Just go ahead and write some code for a derivative of a function, any function, doesn't matter what the function is. This is how general this is. So write a code for a derivative of a function at x for some non-zero value of a. So here's something that we haven't done yet, which is Python, and most, if not all, programming languages allow you to define functions which take functions as an input. And so here's an example of this. And here I wrote more comments, so hopefully Anonymous doesn't get annoyed with me. But here's my derivative, which is a finite derivative, which is just the f in is just referring to the fact that I'm not ever taking this limit. I'm just going to evaluate it for some finite a, okay? And so here I describe a bunch of stuff. My x at f, my final position is x plus a, my initial position is x minus a, the difference between the two of them is 2a, right? And so this function takes in f, some function. It takes in the position where I want to evaluate it, and then the value of a. And then that's it. So simple. You don't believe me? Just try it out. There, you wrote, look, like this is, I don't know, like 15 lines. The only meaningful lines are 1, 2, 3. In fact, I could have done it in one line. I could have just printed out the difference between these with some proper parentheses divided by 2a. Super easy. So give it a whirl, okay? So like I said, the hard thing in calculus is proving that the derivative of functions, evaluating analytically the derivative of different functions. So I'm giving you a table. I'm not here to teach you calculus. What I'm here is to basically show you how to evaluate these things numerically. So here I'm giving you a table of some useful known derivative, the derivative of some functions, which are very common that we use in physics and in other fields all the time, that we're going to cross-check. Some of these we're going to cross-check, okay? So C here is a constant, just some constant. Doesn't matter what it is, okay? And so here, the first one is the derivative of C with respect to X is equal to 0. This one is super easy to see. I mean, I should maybe let me put this back 1 second. While I'll do so, I'll open up my iPad while I see if there's any questions. Do people have any questions about this, like this code? Do you believe me?
Not seeing any yet.
How many people haven't seen calculus? Let's put it that way. Has anybody not seen calculus? Has everybody seen calculus? Yes. Philip has seen calculus. I could have guessed that one. Anonymous. Good. All right. Maybe I'll skip ahead if people. Yep. Abby says yep and sticks out her tongue. Or their tongue. Very sassy. All right. Okay, so yeah, and Adriana has a bit of code. Wonderful, good. All right, so fine, whatever. You guys have seen calculus, and maybe we can skip ahead a little bit. Okay, so here's some known functions, right? The derivative of sine is going to be proportional to cosine up to a constant, which depends on the argument, right? The derivative of log is proportional to, it's equal to 1 over x. This is just some polynomial. You just lower the power of the polynomial. Cosine gives you back negative sign up to a constant that is multiplying the argument. The exponential just brings down the coefficient in the argument of the exponential, and it gives you back the exponential. All right. So if you haven't memorized these functions, you've taken calculus, memorize them. It's my advice. And so what we're going to do here is not just write code, but also this code requires a finite a, right? We can't take a to 0. And the reason why is because if I set this to 0 and I divide by 0, I'm going to get Python is going to spit out nan, which means not a number, okay? So we can't actually take a to be exactly to 0. So what we can do numerically is take a to be smaller and smaller and smaller, and see that our result is converging to some answer, okay? And so what we're going to see is at least a visualization that our result is converging to a desired answer. And in addition to this, we would like to introduce some quantities that give us a measure of the error of our result, okay? And the way that we can do this is that if the result is independent of a, then the derivative with respect to a must be 0, right? If we reach a point where it doesn't depend which choice of a I take, right, then its derivative with respect to a should be 0. And so the way that we can do this is by following the steps, okay? We can calculate first the derivative at a and delta a, just from this. Then you can evaluate, so at some value a plus delta a, so some non-zero delta a, okay? And then we can calculate the same function, the same derivative, but now at a smaller value of a, okay? So if the result is independent of a, then the difference between these two should be 0, right? Because I've just chosen one a versus another value of a, which is smaller. And so what we're going to do is just essentially take the difference of those and scale the difference by delta a. That's going to be essentially the derivative, right? That's the derivative with respect to a. All I care about is the magnitude. I don't care about the sign. So I'm taking the absolute value, and I'm going to scale this by 100 so I can see it. I don't have to scale by 100, actually. I could have just left it. But all right. So I'm going to call that sigma a, okay? That's going to be my error. And so now let's test the convergence. That's exercise number 2. You've written your code for your derivative, then let's test that you're taking derivatives as a function, and that as a function of a, you are converging to the right answer, all right? So let's take a to go from some tiny little number. So I could have done this, I should have done this the other way around, where I start from a big number and I take it to a tiny little number in steps that are, going down. But instead I did it the other way around, perfectly fine. And I'm going to fix x, the argument of the function, to be 1. All right. So a, I'm going to set it as an array that goes from power 10 to the negative 5 all the way to 0.5 in steps of 0.03 of 10 to the negative 3. Sorry. You can pick whatever size you want for the steps in a. I just picked some random number. And so we're going to test our numerical derivative with these with these functions, sorry, an exponential, a log, a sine, a cosine, and then some polynomial. All right. Since you've taken calculus, you should be able to know exactly what these should be, right? And so go ahead and test them out. So here's my results. So I'm getting the derivative of the exponential, the numerical derivative of exponential divided by 2a, okay? And here, what I'm plotting on the horizontal axis is a, and here I'm seeing the derivative on my slope, right? So the derivative on this curve as a function of a. You see that my values are going from large a, it starts to converge. This starts to go down and down and down. And this result, right, is converging. So remember, I picked x to be equal to 1, right? And I know the derivative of an exponential is equal to the exponential. When I evaluate x equals to 1, this should give me back the result of x equals to 1. And you see that indeed, it's as I take a to be smaller and smaller and smaller, I am converging to the value that is this line. This figure is a little bit loaded. So ask questions now, make sure that you understand them, because you're going to have to reproduce this on your own. Or is it super clear? Does everybody know exactly what to do? Yeah, we can go over it. So we can go over it again. Very good. So I'm fixing x to 1, right? And we're gonna make plots for each one of these functions. First, I'm looking at the exponential, okay? And I'm varying a in this region from 10 to the -5 to 0.1 in steps that are tiny, okay? And so what I'm plotting is delta a of the exponential divided by 2a. Really what I'm plotting is the output of my function that I defined before, this thing, this fin deriv. Okay? So I'm just plotting this, the output of this for some function which I picked to be an exponential, one value of x, which I'm always fixing to be 1. I'm just fixing it to 1, okay? And then varying a. That's what's being plotted in red, all right? This black line that is over here is the result that I expect from calculus. Having taken my calculus course, this is what I expect to get in the limit that that a goes to 0. And you see that indeed it is agreeing. And in fact, you can see that even for some large values of a, the difference is not that big, right? Like, look, this is 2.722, 2.721, 2.720, right? So the difference is at the fourth significant figure. So it's a sub% error. That's pretty good, right? So it's converging pretty fast. It's just I've zoomed in quite a bit so you see this deviations. What is being plotted on the bottom is the derivative, right, that I'm plotting, with the difference between that and the nearest step in a. All right, so I'm basically grabbing some point like right here, and I'm taking the difference with some point that is right here, and then I'm dividing by the distance. That's all this is. So it's just the derivative of the slope. So sorry, so it's just the slope of this curve, right? The instantaneous slope of that curve. And then I just multiply by 100 to see it. And you're seeing that indeed the slope is going to 0, right? And you can see it on the data too, right? You can see that like, oh, if I take a small change in a, there's a big difference, right? But here, there's a diminishing return, right? As you go to smaller and smaller a's, the result doesn't change much, right? You're reaching some convergence.
Yeah. Adriana has a question about the numerical code for finding a derivative.
Yes.
They ask, whenever we type in f in the program, what do you type in? Sine of x?
It depends on the function. So here I'm putting the exponential. So let's look at my code. Again, all my codes are available. Sorry, did you have a question? Do you want to follow up, Connor?
Yeah, well, I think I think they're more asking about the syntax, like, because I think you can use either lambda functions for this or just define a function in front of it and then put that in directly.
Yeah, very good. So the way that I defined it is very simple. So here are the basic functions that I'm using, which exist in NumPy. Okay. So this is a square root function, this is a exponential, this is a sine, cosine, log, and then I define a polynomial function, which are exactly the ones that are considered in, where was it? Over here, right? So we have exponential, log, sine, cosine, So there they are over here. I added also a square root function, but the polynomial is exactly the same one, okay? And then, as I said, my finite derivative, right? It takes in a function. The syntax here is that there's a local variable. So it's whatever f, whatever f you feed it is going to go all the way through, okay? So now let's look at the places where I use this function. So I just search for fin underscore derivative. And you see, aha, here's a little example of me using this. And look, in the first place, what I have is exp, which was my exponential function. And that's exactly the code that I used to generate this figure, this first figure. Okay. So then if you look at, and you see this exponential region, this exponential part. And then you see, I have now a sine one, which I'm doing the same thing as before, right? But now it's sine.
All right, I think they understand now.
Awesome, cool. All right. So anyways, so this is the kind of figures, right? We're generating. Let's basically, here are all the figures that I've generated now because I just have a looping code over all these possible examples. So I did one for log where what we should get is 1 over x evaluated x equals 1. In other words, 1, right? And you're seeing, again, this converges really fast, right? Like where it's up, again, the error is at the fourth significant figure. And then the error, which is a sigma, right, it's just tiny. Cosine, the derivative of sine is cosine, and indeed I am getting that with enough determinations of a, I'm getting something that is close to, it quickly approaches to cosine of 1, again with tiny errors. Same thing, the derivative of cosine is equal to negative sine, and that's what I'm getting. I'm converging to negative sine of 1. And if I take the derivative of a polynomial, then you have to take the derivative of this guy plus the derivative of this guy. This is x cubed divided by 6. That's also the derivative of that is going to be 3 over 6, which is 1/2 times x squared plus x, the derivative of x to the fourth is 3x cubed. So sorry, 4x cubed. And so then the 4 and the 8th gives you 1/2, and you have 1/2 plus 1/2, both evaluated at everything evaluated at 1. So you have 1/2 plus 1/2, which is equal to 1. And so you end up getting this. Again, everything is at the fourth significant figures. So this is how you test convergence, right? So and convergence just means exactly this, that the result is converging to some value for sufficiently small values of a. So, I mean, it could have been that if we had algorithms that were this fast and easy, perhaps a lot of the calculus that we learned, we wouldn't have learned it as well, because maybe we would have relied on computers. But there's obviously a lot of need to having analytical results, not just numerical results. But it's really nice to see that analytical known results can be obtained really easily numerically. So, all right. So hopefully that's super clear. So that's the set of exercises for 2. Well, now let's do something a little more interesting. So set of exercises for 3. Now that you've obtained you've tested your code, right? It's working, it's beautiful. Now let's test it against the derivative of known functions, but as a function of an x, not just at one particular point, right? And what we find from these figures, right, is that if you make a sufficiently small, you essentially have no error, right? This is just unvisible. This is not visible by by our eyes, right? So if you fix your a to be sufficiently small, and I picked it to be 10 to the minus 3, you can't see any difference between what we would expect analytically versus what we are getting numerically, okay? So in this next set of exercises, what we're going to do is that we're going to fix a to be some tiny number, okay, 10 to the minus 3, and then make plots of the functions that we're after and their derivatives as a function of x. So on the horizontal axis in both cases is x, right? We're just keeping a fixed now. And then we're taking the derivatives, and my blue line is my numerical result, and then the green points are what I expected from calculus, and lo and behold, it's right on top of it, right? Nothing funky. And so once you've written code to make these plots, right, then you should be able to make other plots. So here's the one for sine. So the sine, the derivative of sine is cosine. And my numerical results exactly match what's out there in what we know from calculus. If this may seem boring to you, it's important to do these simple exercises to cross-check everything and make sure you're really confident on what you're doing before you go and do something more complicated, right? So, you need to make sure that you're doing this very well before you jump into something harder. And so here is the same thing for cosine, right? Cosine, the derivative of it is equal to negative sine. And look at that, it looks beautiful. And you could do the same thing with the polynomials, but the story is basically the same. So maybe we can stop here for a second and see if there's any questions before we start introducing differential equations. At this point, all we've been doing is just taking numerical derivatives of functions, which is great, but it's not the most interesting thing yet. So we got to build you up to doing more interesting stuff. Let me see, how am I doing on time? All right. I think we'll cover a little bit and then we'll call it a day. But no questions so far. This may be simple. Yeah, I think this is simple, conceptually simple. I think it's just a matter of just rolling up your sleeves and getting to write your own code, right? And then spend hours debugging because your results won't look the same as the figure in the first place, right? So, all right, if I don't see any questions, let's move on. All right, so we're going to do differential equations. We're going to start with first order and then jump into second order. So it's going to be fun. As I said, this is going to lead for us to be able to construct models of infectious diseases. So, so we'll get there. I see there's a question now about the error and the standard error equation. What are the symbols? Yeah, let's go back. This right here. So I just defined the sigma. It doesn't mean anything. It's just basically, I could have just defined it as it's essentially just a derivative of the slope right here. Sorry, it's a derivative of this figure, right? I'm just taking the slope of this figure right here and multiply it by 100. And I just called it sigma because I'm not that clever. There's not that many symbols I can come up. I could have probably called it something else, but that's what I called it at the time. So delta A of f, right, is divided by 2a is just a derivative, one value of a. Delta A plus little delta of f divided by 2 plus little delta is equal to the derivative. Oh, there might be a typo. This 2 might not be there. Yeah, I don't think it's there. Okay. That won't change anything though. It's just going to scale everything by a factor of 2. But okay. Yeah, I don't think that should be there. I don't know if this propagated to my, wait, did I define it this way? Oh, I did define it this way. Oh, no. It is there. No, never mind. It is right. It is right. But okay, let's look at it here. Delta A f divided by 2a is just the numerical derivative of f at some value of a, okay? This is exactly the same thing, right? I just replace a with a plus delta, where delta is just some little value. It's just the next step, which in practice, what I'm doing is I'm setting it to be 10 to the negative 3. Because that's what I defined the distance between each point and a. All right. So that's what the little delta is. You can just imagine it's just a placeholder for 10 to the negative 3. And then I divide by 10 to the negative 3. So without this 100, this is just a derivative of the derivative of f. So it's the second derivative of f. The 100 is just because I put it in there. So sigma doesn't have any meaning, any real meaning, except if the derivative of f is independent of a, then the derivative of f evaluated one step, another point in a, will give you the same results. Does that answer the question, Anonymous? Anonymous. I don't think I've ever, good. I don't think I've ever used that word as much. I think I probably said anonymous less times in my whole life together than I've said it in the last 4 weeks. Okay, fun facts about my life, I guess. All right, let's move on. So differential equations. All right, so you know how to take a derivative, right? Now everybody loves derivatives. Wonderful. So differential equations are equations that relate one function or more functions and their derivatives, right? So you can have multiple functions that are related to derivatives of functions. So the simplest example of a differential equation is this one, where you have a derivative of f giving you back some function called g of x. So in general, differential equations can be more complicated. Basically, all the important equations in physics and in science, I can't think of an example or a counterexample actually of what I'm about to say. They're either differential equations or integral equations. Or it can be at least written as differential equations or integral equations. Okay. So the simplest one that you learn in physics is Newton's force law. So F equals ma, which is the force acting on a particle is equal to its mass multiplied times the acceleration that it's experiencing. Well, the acceleration is the rate of change of the velocity. The velocity is the rate of change of the position. And so the acceleration is a second rate of change of position with respect to time. And so F equals the mass times the second derivative of x. Wave equations are also differential. Schrodinger's equation is a differential equation. Maxwell's equations can be written as differential or integral equations. So basically, most of science requires us to solve differential equations, and the rest of science requires us to solve integral equations. So although finding solutions analytically can be a daunting task and requires quite a bit of calculus, finding numerical solutions is super easy. And everything you've done already is enough for us to find solutions of differential equations, at least of the first kind. And I'm gonna show you this in just a second. In fact, I should connect my iPad for this. So it just requires a little bit of algebra. And right, the catch is always that we're doing everything at a finite separation, right? The tricky thing is that in calculus, we always define everything in the limit where the points are separated by 0. And so that's tricky, right? That is complicated. But if we choose to continue to consider things in a finite spacing, then a derivative like this gets translated to the difference of f evaluated at a minus f evaluated at right, and we just keep a fixed, right? Then all we have to then do is just multiply both sides by 2a. So I get that and then I'll subtract both sides by f x minus a. And so voila. So then I have that f evaluated at the f value at some later time is equal to the original f value, right? Plus a shift, which is, this is connected to the rate of change, right? The rate of change of f is equal to gx, right? And so if you give me some original value of f and I know what g is, then I can give you all the values of f at any point, right? So I need the first, I need f at some first instant, and I need to know gx. But if I know those two things, then I can evaluate, I can find all the possible values of f. How simple is that? And so here I just rewrite things a little bit. So I say, let me rewrite, if I rewrite this replacing x with x naught plus a, so then the original point is x naught, then you can see things perhaps a little bit differently. So I mean, it's the same difference. And since I've used x naught to be some generic variable, right, I can relabel it as x, right? So all I've done is just shifted my variables. And so given some original value of x and g, then I can predict what f is at x plus 2a. And so imagine that you're given some original value of f naught, right, at some original point. Then I can determine the next one by just doing just applying this equation, right? So I get that at some later time. Well, we can just, let me just share the slides next to my, so I have my original x equals 0. So I know f as 0, right? And then I just apply this equation, which I just argued can be written as that, right? I don't like that square. Let's make it again. There we go. A little bit better. All right, so I have some original point there, and then at some later point, let's say 2a, right? Then what I'm evaluating is I just use this equation, right? So at 2a, I pick x was originally 0, this is 0, this is 0. And so I get that this point is now, this is equal to f of 0 plus 2a g of 0 plus a, also known as just g, right? And so then at some later point, I just apply this equation again, right? And then the next point here is going to be determined from the previous point, right? So all I have to apply this shift here is, it's just going to be 2a g of a plus the previous one, which was 2a, so it's going to be 3. And so then this is going to be f of 0 plus 2a ga plus 2a g 3a, etc., etc. Okay. And I could have just written this as I did in my slides, recognizing on this thing right here. This thing right here is nothing more than f evaluated at 2a, right? So basically, you just have an iterative procedure for getting any point given the previous point. And so if you have an original point, you can get the next one, which gives you the next one, which gives you the next one, gives you the next one. So you don't actually have to spit out all these equations. You can just write a loop that does this for you. So cool. Very simple, no? All right, so let's put it to practice. Exercise number 4. Why wouldn't you use the original function that you took the derivative of? Oh, no, yeah, very good, very good. Okay, Anonymous is asking a very good conceptual question. What is this really solving, right? Like, right now we've been considering cases where we know the function that we're after and we take the derivative, right? And then we can get the right-hand side, right? So maybe let me take this out. So let's say the first things that we did was taking derivatives to find g. Okay, so we had this we knew. This we didn't know. Right? That's what we were doing before. So you give me some function and I take the derivative, right? Straightforward. That's easy. And I can take as many derivatives as I want. Very good. What we're jumping into are cases where you're doing the same thing, or we're considering the same basic question. But in this case, we know this. But this is the thing that we don't know. So it's conceptually harder. We know that some function, if you have a derivative acting on the function, it will give you back another function. And we know what this function is. But we don't know what this function is. Does that make sense? So in the case of, let's say, a practical case, right? Of Newton's law. So you have this thing, right? So in this case, you can imagine that I have some object, let's say I have some ball, and I know that I hit it, with my bat, and I apply some force, let's say. So the question would be that we would know the force, but if we wanted to determine its trajectory, we would have to solve this equation. So depending on the force, this is straightforward. We can do this analytically. Some cases, it's not so straightforward. Does that make sense? If you're finding the original function from the derivative of it, couldn't you just think about it as an integral of the derivative? You mean, can I just get the, yeah, you can get, you could do that way too. Yeah, so we'll get to talk about integrals. I don't want to jump ahead. But at least hopefully everybody understands this task, right? So we're going to think about differential equations and give you a simple example first. Life is going to get a little trickier, right? But the idea, right, is that you have some known function. So some known function, and trying to solve for an unknown function is who you know that their derivative is related to a known function. All right. So let's continue ahead. So this gives you a procedure for doing this. Then the next thing that you can, Diana, you're getting ahead of me. We're gonna give you lots of examples. So you're gonna test it out. Here's an example. So, so the simplest way you can do this is to write a code for obtaining f for a range of values of x given some known function g. All right, and some original value for f. And so basically it's just applying this iterative procedure within a for loop. All right. And so here's my code for doing just this. So I explain it in some detail. And maybe what I'll do is that I'll stop here, and instead of jumping ahead, making sure that everybody gets this, and then we'll pick this back up on Monday. I think we're good in time. So let me walk you through this. So the code, so here I'm solving a first order differential equation. I solve this equation by discretizing the derivative, solving for the next step algebraically, as I just did with you, which I can equivalently write in this form. And then I have some list of x's, my original value of f naught, the function that we want to feed into it, and then my step in x. And so I'm gonna spit out my content in a list, which I'm calling fs, okay? And I just write a loop that just goes over the possible indices enumerating this list of xx. All right, and so I have some list. So I've in general, this takes in some list, which is x0, x1, all the way to xn. All right. And so I'm looping over indices, which I'm calling I0, where this is equal to 0. For this one, basically I0 is just the subscript here. So on this one will be 0, this one will be 1, all the way to n. All right. And so here I'm grabbing the previous element of the list. All right, so this is a list. It grabs the previous element. That's what -1 does. It grabs the last element in the list. So here, if I naught is equal to 1, it just grabs f0, all right? And then I shift that by the amount dictated by the differential equation. And then I add to the list, I append to the list f0 plus df, the little shift in f. And then I return fs. So I suspect that some people may have questions about this. So feel free to ask them now. No shame in asking questions. And I left a lot of comments there. Hopefully they're helpful. All right. Yeah, my code is on Dropbox. The question is whether my code is in Dropbox. It is. All right. So once you've written code for this, then the idea is to test this out, right? And let's test it out with some functions that we know how to solve. That's with everything, right? So the derivative of f is going to be some function that we give you, g of x. And the first one is to call it an exponential. Well, the derivative of exponential is equal to an exponential, so we could guess the answer here. And so here we know the answer to the solution of this differential equation is an exponential, and indeed this is what I'm getting. And here I'm plotting what the derivative, the input function is. So Anonymous is confused on the list. So good. I see the confusion. So I'm overriding. So the confusion is that I have f0 here and f0 here. So f0 is an input. I put it as the first element, okay? And then the next time I say, no, actually f0 is this thing. This has already been stored into this list. This numerical value of f0 has been stored. But the symbol, the local variable f0 has been overridden. And so f0 now has taken on a different meaning. The first component of fs, it's just some number, it's been stored. But I've overridden the meaning of f0. Does that make sense now, Anonymous? So I'm overriding the definition of f0 here. Hopefully that makes sense. All right. So we tested with an exponential, and then the last one, the last two examples are sinusoidal functions, because we know that the derivative of cosine should be negative sine, and we know the derivative of sine should be cosine, and so we're just testing these ideas. So again, the tricky thing here is that what we're given it is a derivative, which I gave sine, and we know that the derivative of cosine is equal to negative sine. So because I'm given a sine, that means that the function that we're taking a derivative of is negative cosine, and that's indeed what I find. And then the driving, and also notice I have to give an original value of f, which I chose it to be -1.
Anonymous is wondering if it would be better to make a new variable instead of overwriting it.
Sure, yeah, you could do that. So logically, there's nothing wrong with what I did. It's just conceptually maybe trickier. But yeah, you can call this f f of 0, let's say you feed it f0, right? And then here you can call it f1, right? And then just call this one over here f1. That's perfectly fine. Yeah. I tend to override my variables quite a bit, but there's no, as long as you do it carefully, there's no problems, but it can lead to mistakes if you're not careful. All right, so we covered negatives, that case, and then the other case that the last one is the derivative function is cosine, and so it should get that the original function is sine. I fix it so that at x equals 0 is equal to 0, and so indeed I get sine. Cool. All right, that's it. That's all I got for today. So you learn a little bit about calculus. You learn about taking derivatives. You learn about how to solve first order differential equations. Guess what? We're going to do second order differential equations Tuesday. It might be a short lecture because I'm going kind of fast. And then Professor Ted Rogers is going to pick it up on Friday and start talking about infectious disease models. And then I think he might talk about cryptography, which should be fun. And then at some point, Connor has to do his fitting exercise.
Yeah. I was thinking we could get some cryptography in with the marbles exercise as well.
Yeah, cool.
Because we used RSA for the guesses. Could have them implement their own.
Okay. I won't hold you back. So do you have do you want to remind people about the marble exercise?
Yeah, sure. Right now we only have 21 guesses. It'd be great if we could get some more. So like if you could maybe ask your family members, your friends for their opinion on how many marbles they think is in there.
You want to put do you want to put the link on the chat?
Yeah, that's a good idea, actually. Let me find it real quick.
Anonymous is asking if I'll be back after Professor Ted. I will. I don't know to what extent just yet. We'll see. But like I said, I'm going to be lecturing separately on nuclear physics. So people are welcome to join that if you're interested in learning about that. And I have other surprises that I'm not going to tell you about. But you will be hearing from me again, for sure. But definitely don't check out Ted's lectures. They're going to be great. So you put in, so maybe let me share the screen to see the problem. So the problem that your challenge, if you choose to accept it, is to guess the number of marbles in this jar. And there's a link up here. tomatoid.github.io/marble guess.
Yeah, it's in the chat as well. It should be.
Yeah, it's in the chat. I just was reading it aloud for people at home that are watching on YouTube later.
Ah, that's a good idea.
Yep. Is the mentorship timings going to shift a bit, or do I have to stick to recorded videos? So I don't know exactly what you're referring to. I send out an email to, because I don't know who you are since you're anonymous, but I send out an email to my mentees, and my lecture is going to start Monday. In fact, I need to talk to distance learning folks to coordinate this. So maybe Kevin can stick around a second after this. But will be there will be Monday at 1. I think it's 1 p.m. Eastern time, and so those are the times that work the best for us. And there's people from all over the world. So I know that some of you, the time won't work, but we'll make the videos available for you. Okay. All right. Maybe let's call it a day. Hope everybody's having a good week and that they're staying safe in their corner of the world. And we'll be seeing you on Tuesday. Okay. Take care, everybody. Bye. Should I stop the recording, Kevin, or do you want to take a stab at it? Maybe I'll do it. Hopefully I don't break it.
I could do it and take the blame if it messes something up. Oh, there you
No,
go.
yeah. All right. Well, all right. Maybe we'll call it a day for now. Okay.
Yeah. All right.
All right. Take care, Connor. Let me know when you update the poster and I'll check it out.
Yeah. All right. I got to do that sometime, but we got a relative coming over this weekend. I got to clean my room, which who knows how long that'll take.
Sounds good.
So
whatever
yeah,
time
hopefully
it takes.
I got to make time for it, but
when is it due?
I think it's due on Tuesday, which is my birthday. So that's a nice birthday present.
Sounds good. Cool.
Yeah.
All right. Well, let's catch up later. Okay. Let me know whenever you update it. Okay.
All right. Yeah. I'll let you know.
All right. Take care.
Bye.
Bye.